Hi, I'm Kate Saenko, and I'm a faculty member at Boston University and at the MIT-IBM Watson AI Lab. And today I'll be talking about mitigating dataset bias. So what is the problem of dataset bias? Well, suppose that you're training a network to detect pedestrians, and your training dataset comes primarily from California, where the weather is sunny and people are wearing light summer clothes. And now, after you've trained this network, it's being deployed in New England in the winter, where people are wearing heavy coats and there's snow on the ground. So because your training data looks different from your test data, your network will likely have worse performance, will have missing detections in this case. And this problem happens very often in computer vision, and it's commonly referred to as dataset bias or domain shift. When does dataset bias happen? Well, as I already mentioned, it can happen when we train a model on labeled data from one city or geographic location, and then we want to transfer it to another city. Or maybe we train on labeled data from the web and we want to transfer the model to a robot. Or perhaps we're training in simulation and transferring to real-world data. So in all of these cases, dataset bias from training to test will affect the performance of the model. However, we can also think of a shift from one demographic to another, where the training data might contain primarily images of males of a light skin tone, but at test time we're given images of darker skin tone and more females. Another example is, suppose we're trying to recognize weddings and our training data comes from North America, where the bride and groom may look very different than in images of weddings from India, for example. So in all these cases, the problem with domain bias is that it reduces the accuracy of the trained model. Let's take a very simple case, which is just MNIST digit classification. We know that if we train an MNIST and test on MNIST, we'll have very high performance, say 99% accuracy. But what happens when we train on a different digit domain for the same task of classifying 10 digits and test on MNIST? Here we're training on street view house numbers. You see that the performance drops very significantly because of this domain shift. And even if we trained on USPS, which is a more similar digit domain, which also is black and white and also has handwritten digits, it still causes a large drop in performance on MNIST. And by the way, if we switch and train an MNIST and test on USPS, performance is still very poor. And this problem also happens in other tasks. Here we have a semantic segmentation problem where we want to train the model on simulated game images because we have a lot of training data we can get easily from games. And then at test time, we want to use the model to predict semantic labels such as people, roads, and so on real images. And here you can see that the predicted labels from this model that's trained on synthetic data are not very good at all, and it suffers from a large drop in accuracy compared to what it was obtaining on the training domain. So let's define this problem more formally. So we have a source domain where we have lots of labeled data. Xi are the inputs and Yi are the output labels, and this data is distributed according to some source distribution ds. And we also have a target domain which has unlabeled data, Zj, and it is distributed according to a target distribution dt. Sometimes we'll assume that we'll have a few labeled examples in the target domain, but for the most of this talk, I'll assume no target labels at all. And so our goal is to learn a classifier f that achieves a low expected loss under the target distribution. So what causes poor performance in domain bias situations? There are two main reasons. The first is that the training and test data distributions are different. And you can see in this example where we have the blue points are from one digit domain and are used to train the model, and then that model is used to extract these features, which we visualize as a t-SNE embedding. And then the features in red are those extracted from a new domain of digits. So you can see that the two distributions are, in fact, very distinct. Another problem is that the source trained model, the one that's trained on the blue points, may lack discriminative features on the target test points. And you can see that because the red points are not as well clustered together. There's less space between the different clusters in the red target domain. Fortunately, there are techniques we can use to help us deal with this dataset bias. And first of all, just some simple techniques are, of course, that we can collect label data from the target domain, but in many cases, we're not able to do that, or it's very expensive to do that. And so another thing we can do is use a better backbone network, which tends to reduce domain bias. We can also use simple technique of batch normalization, or domain-specific batch normalization tends to help. We can combine that with instance normalization, which also tends to help. And another useful technique is data augmentation, or methods such as mix-match, which can be used to reduce the sensitivity to domain shift as well. And we can alternatively also use semi-supervised methods such as pseudo-labeling to propagate labels from source to target points. And finally, and this will be the focus of the rest of my talk, we can use domain adaptation methods. So the outline of my talk today is as follows. I will first talk about some at this point, fairly traditional techniques based on adversarial domain alignment, both in feature and pixel space. And then I'll talk about some limitations of these techniques and how we can solve them. For example, limitations of strong alignment, and also how we can respect the class boundaries better, how we can use feature disentanglement to measure distances between domains, and also I'll talk about how to deal with category shift in addition to dataset shift. All right, so let's start with adversarial domain alignment. Here we have a source dataset with labels, and for simplicity, let's assume just two classes. And we feed these images into our neural network, which we split into the encoder part, which is everything except for the last classifier layer. And then we visualize the features extracted from the encoder, from the source domain. And we'll train this model using just regular backpropagation with a classifier loss. So the classifier will learn a decision boundary, which we can visualize in this feature space. Now, suppose we have unlabeled target data, and the target data has the same categories as the source, but we don't have any labels for those. We can take our encoder CNN and generate features for the target images, but because their distributions are different due to this domain shift, the classifier will be less accurate on the target points. So in adversarial domain alignment, our goal is to align these two distributions, the source distribution and the target distribution. And the way we're going to accomplish that is by adding another classifier. We call this the domain discriminator. It takes as input points from both source and target and tries to predict the domain label of the points. So it tries to discriminate between the two distributions. And we can train this with a GAN loss, where we alternatively minimize the loss of the domain discriminator. So we train it to distinguish the two distributions. And then we switch to training the encoder to generate features that increase the error of the domain discriminator. So it will cause the discriminator to not be able to distinguish the two domains. And so the encoder can do this by essentially generating target points that are distributed very similarly to the source. And then we achieve our goal of aligning the two distributions. So in this case, we hope that now our classifier, which is also being trained at the same time, we're optimizing both losses at once, will have better performance on the target points. We can see an example of this here. So on the left, we have our two-digit domains from before, the blue source and the red target before adaptation. And then after doing this feature alignment, we can see on the right that indeed the distributions are now very similar, and the red and blue points are very much aligned. And so this is done using a technique from a paper by Gagne and Pitsky, and they showed that this also improves classification performance on the target digit domain. Okay, So we can do this also, the similar kind of alignment, but in image space directly. For example, let's suppose that we have, again, a digit domain with labels, which comes from Google Street View numbers, which look different from our target handwritten MNIST digit domain. And so instead of feeding images directly into our feature encoders, what we can do is first train an image-to-image translation model to translate the source images to make them look like they came from the target MNIST domain. So this is a model we proposed in ICML 2018, and what it does is it uses a conditional GAN to make this translation from source to the target domain. And now the nice thing about this is we now will have label data that looks like it came from the target domain, so we can just train a model on this directly. Or we can additionally add feature alignment, just what I've described earlier, on top of this pixel space alignment with the same kind of feature alignment technique that I just described. So we can do both, and actually we found that doing both can help with improving accuracy on the target. So I'll show an example of this in action here. The two domains are the synthetic game domain. This is a Grand Theft Auto game. And the goal is to segment the images into semantic categories, and our test domain is coming from a real data set called cityscapes. And so here is a video that shows, in this case, the model translating from real to synthetic, and you see how it makes the real cityscapes images look like they came from the game, from the Grand Theft Auto game. So it makes the colors brighter, it changes the textures of the road and other textures of the background as well. Okay, so far I've showed you how we can do image-to-image translation if we assume that we have a lot of unlabeled data in the target domain. So the model that we used, which was a modified version of CycleGAN, essentially assumes that there's lots of unlabeled data in both the source and target domain so that we can do this translation. But what if we only have one or just a few images of our target domain? What can we do then? Well, something like CycleGAN isn't going to work very well. So we try to address this problem, which we call few-shot domain translation, in our ECCV 2020 paper called COCO-FewNet. So again, the problem here, we call it few-shot unsupervised image translation, which aims to translate an image to unseen domains by leveraging just one or a few input image from that domain. We call this the style image. So suppose we have training domains that we see here. And so we train our model, and then at test time, we receive a new style image from a new unseen domain. And our goal is to translate content images from a training domain to look like it came, the style-wise, it came from an unseen target domain. So to illustrate what I mean, I'll show you an example. Here we have some content images of different animals. And so our goal is to take these content images and translate them based on a given style image. So here the domain is essentially the species of the animal. And the content that we want to preserve in the translation is the pose of the animal. So here's the output of our model, and we can see that it preserves the animal's pose, but it makes them look like they are from this new species. And again, here the style image comes from a domain that the model did not see in training. The interesting thing is you'll notice that in this middle row, it even preserves not just the pose, but also the age of the animal. Here's another example. Now this is with birds. And again, we see that the model is able to combine the style from an unseen domain with the content, the pose of the bird from the input content image, and generate a translated image that looks like the same pose of the content, but the new style. We compare this with previous work, which is called FewNet. And here we can see that based on the input style and content images you see here, the previous work, the previous model is not able to preserve the content or generate convincing style. So it's failing to translate. Essentially, it's not able to handle the changes in the poses of the animals very well. Whereas our model is able to preserve the pose, even though the style and the content have very different pose, it's able to translate the style onto the pose of the content. And actually, the difference between FUNIT and our model is primarily in the way that we encode the style encoding. So in both methods, the inputs are a content and style image, and they're fed into a content encoder and a style encoder, and then the style is captured in some parameters that are fed into an image decoder along with the content code to generate the output image. So the difference is in our approach, COCO FUNIT, we have a new type of style encoder that we call COCO, or content condition on content. And we call it that because, in fact, it is conditioned on the content image, unlike in FUNIT, where the style encoder only receives the style image and does not receive the content image as input. So here are the details of the content encoder, COCO. Here we see that both the content and style images are encoded by extracting convolutional features and then mean pooling and then combining using an element-wise product. But one thing we introduce here as well is a constant style bias that we learn globally for the domain, which also helps our model preserve the content of the image better and combine it with the style in a better way than the previous model does. I'll show you some more examples. So here we have an input video that you see on the left of a dog, and then we're translating the same video into different styles, including other types of dogs or even a fox in the first case. Here's another example where the input content videos of a bird, and we translate that into a new style of a bird based on each style image that you see above. You can see that the model is preserving the style and the content fairly well. Okay, so now that I've talked about adversarial alignment, both in pixel space and in feature space, I want to talk about some of the drawbacks of this technique of adversarial alignment. And I'll focus more on feature space because it's a little bit more of a general method, because pixel space alignment can be challenging between domains that have a large shift between them. So I'm going to focus on feature space alignment from now on, and I'll talk about some of the problems that we can run into with this adversarial feature alignment technique. So the first problem that we might run into is that this kind of strong alignment between the source and target could actually hurt us. And I would argue that in some cases it does make sense to do this strong feature alignment. For example, here we have two domains where the source and target are essentially the same images, but in the target we have artificially added fog. So we can actually find matching pairs of images between these two domains and perform the alignment very well. Essentially, the model would just be throwing away the fog from its representation to align the two domains. But on the other hand, if we had two domains that have very different scene layouts and the numbers of objects are different between the source and target, maybe the locations that objects tend to be in is also different. And here we're doing a task like, let's say, object detection, where objects can be located anywhere in the image. So here it may make less sense to do strong alignment, because we could end up trying to align images close to each other in the feature space that have very different semantic scene layouts and different numbers of objects and different types of objects, so we would be losing information. So how can we still transfer knowledge from our source data set to the target in this case. So what we proposed in our paper from CPR 19 is to relax the alignment constraint. And we're still going to do feature alignment, but it's going to be a weak alignment in this case. And ideally, we want our model to figure out automatically if it should do strong alignment or weak alignment, depending on the two domains that it's given at training time. The way that we handle this issue of relaxing the alignment objective is, first of all, notice that the cross-entropy loss, which the domain discriminator is trained with, where here P is the probability of the input belonging to one of two domains, either the source or the target. The problem with this cross-entropy loss is that the easy-to-classify samples, which are samples that are very different between the two domains, will accumulate significant loss values, so they'll dominate the loss. And the discriminator will be mostly focused on those examples. So instead, what we want to do is we wanted to focus on examples that are more similar across the two domains, which means that they're the harder examples for the discriminator to tell apart. And so to do this, we proposed to use a new loss, which is similar to the cross-entropy loss, but has a weighting by a new term f of pt, where pt is either p if the domain label is 1 or 1 minus p otherwise. And the weighting f is essentially placing a higher weight on harder examples. So these are the examples that are most similar across the two domains. And in our paper, we tried various versions of f, and the focal loss worked fairly well for this case. Here are some results using this strong weak alignment technique. Again, our model will figure out on its own if the alignment should be strong. Like in this case, the two domains are very similar. So we're transferring an object detector from the cityscapes data set to adapt it to the foggy cityscapes data set. And the two data sets are very similar in scene layouts. And here our model ends up doing strong alignment. I showed you the feature distributions earlier. And we also see a significant improvement in mean average precision over the state-of-the-art technique at the time. On the other hand, when we have two domains that have very different scene layouts, like this Grand Theft Auto game and cityscapes, the real images, we see that our model here does a weak alignment and is still able to improve performance on the task. So it's able to significantly outperform the previous state-of-the-art on this object detection task on the target domain. So we see from this that weak scene alignment can still be effective in improving performance on the target, despite the fact that we're not fully aligning the two domains. The next idea I want to talk about is respecting class boundaries. You may have noticed that what we're doing is aligning the two marginal distributions over the inputs, and we're doing this without taking into account our task-specific decision boundary. Of course, we're still training the model with a classification loss, but the alignment process itself just uses a domain discriminator, and it does not take into account our task classifier at all. So what's a problem with this? Well, a problem with this is that some of the target features could be generated close to the task-specific decision boundary, which will make them ambiguous and at high risk of misclassification. So how can we avoid having these ambiguous, non-discriminative features in the target domain? Well, the idea here is to respect the class boundaries of our task classifier and use it to actually do the domain alignment instead of using a discriminator like we did before. This technique is called classifier discrepancy. First of all, again, when we look at the task-specific classifier, during training, what we want to do is detect ambiguous target features. So these are features in the target that are close to the decision boundary. And so we want to detect them, and we want to make them less ambiguous. We want to make those features more discriminative. So essentially, we're going to try to push the target points away from our decision boundary and closer to source points. And the result is that in the aligned distributions, we will have more discriminative features and fewer features in this uncertain region close to the task-specific decision boundary. So this method tends to work fairly well, and there's essentially the key is producing two different versions of the same classifier and detecting ambiguous features using the discrepancy between these two classifiers. So how can we, first of all, how can we get these two classifiers? Well, if you look at the papers below, basically one of them just trains different versions of the classifier, and the other one, the adversarial dropout paper, uses dropout on the same classifier twice to produce two slightly different decision boundaries. But regardless of how we get these two classifiers, the key idea here is going to be to measure the discrepancy in their predictions on target points. So that's the disagreement between the output probability of the two classifiers. And the intuition is that in these ambiguous regions, the discrepancy between the two classifiers will be high, and so that will indicate that the features are ambiguous, whereas for points that are further away from the decision boundary, that discrepancy will be low, and so those are the more discriminative points. So this leads us to a method where we essentially minimize this discrepancy in order to align the two distributions. And I'm not going to talk about the results here for lack of time, but if you're interested, I'm showing the reference below and also show references at the end as well. All right, so another way that we can do alignment that respects class boundaries is by using what we call minimax entropy optimization. So again, here we have source points. The blue points are source in two classes, and then we have unlabeled target points. We also assume the same two classes, but we have no labels, and there's a domain shift between the source and target. And we'll notice that target points that lie far from the source distribution, so far from these blue points, will be near the decision boundaries and will have a high entropy of class probabilities. So the entropy of P of y given x for these points will be higher, whereas points, target points that lie closer to the source distribution will have lower entropy of class probabilities. And so we can use this intuition to develop another method that will align the distributions in a way that respects class boundaries. So we do this by alternating two steps. The first step maximizes the entropy of the classifier. And what this does is it aligns the distributions closer together. And the second step will minimize the entropy to cluster target points closer to their respective source points. So this will make target points more discriminative and push them away from the decision boundary. So again, I won't talk about the results due to lack of time, but they are also in the paper if you're interested. Great. So the next thing I want to talk about is feature disentanglement. Suppose that we again have two domains and we want to transfer a model from some source domain to a new target domain. But what we're going to do instead of feature alignment that I showed you before is we're going to use this notion of a disentangled feature representation. So this is something that's been explored in the literature for various applications. And here we can actually apply that same idea to deal with domain bias. So the idea is to learn a representation using a deep neural network, but we want to split our feature representation into two parts. The first part is the domain-specific features. So these are features that will encode things like brush strokes of the painting domain that are specific to that domain, or maybe high resolution textures that are specific to the real photo domain. And so these features will be exclusively encoding something specific to that domain from the input image. And the second part of our feature, we want to only contain domain invariant and task-specific features. So here our task is classifying cars, and so we want these domain invariant features to only capture information about cars, about our task. And so once we've trained our model in this way that it disentangles the feature vector, we then want to only use the domain invariant part of the feature vector to do classification, in the hope that by removing domain-specific information, these features will be less susceptible to domain shift and will perform better. Will have better accuracy on new domains. And so to accomplish this, we propose this model which takes several domains as input. So this can work with multiple domains, not just two domains. And first we have a feature generator which takes the input image from a domain and encodes it as some high-level feature vector. And then in addition, on top of that, we add a disentangler network, which takes that feature representation predicted by the generator and generates two components based on that. The first is the domain-specific feature vector, and the second is the category-specific feature vector. And the domain-specific part is fed into a domain classifier which tries to predict the domain label. And so we train this feature vector with domain classification loss, while the category-specific part is fed into our task classifier that tries to predict the class of the image. And so that's how this part is trained. And in addition, we also add an adversarial loss onto the domain-specific feature vector, which trains it in such a way that the classifier cannot predict the class from the domain-specific feature vector. Right? So we want to do this because we want to remove any class-specific information from the domain-specific part. And similarly, we have an adversarial loss on the category feature vector, which is now trained also to not be able to predict the domain. So the classifier of the domain shouldn't be able to extract any domain-specific features from the category part. And another thing we do here is we add additionally a term that minimizes mutual information between the domain-specific and the category-specific parts of the features. And finally, we use Reconstructor to recombine our disentangled feature representations into the original feature vector that was produced by the generator. And we do this so that we do not lose any information, right? So we want to reconstruct a VIE or autoencoder. We want to reconstruct the original input, so we preserve all the information. Okay, so as I said before, to do classification in a domain invariant fashion, we would keep these category-specific features. But you might be wondering, well, what about these domain-specific features? Are they good for anything? Can we use them for anything? Or do we just throw them away? Well, it turns out that we can use them for something. And in particular, we notice that these domain-specific features will encode, of course, textures and patterns that are specific to the domain, but not useful for the task. So, for example, they encode brushstrokes or other textures or other styles that are specific to one domain. And so we can use these features actually to measure distances between different domains. And this leads us to propose domain embedding, which we call domain to vec, which can be used to project whole data sets or entire domains into a vector space and then measure distances between them in that vector space. So suppose that we get a new data set and we don't have labels on this data set. We want to transfer knowledge from some other data set, but let's say we don't know which data set is the closest. Well, we don't want to manually determine this. So how can we find another data set that has labels that we can transfer knowledge from without manual intervention, just automatically? And so we propose to use this domain embedding using our domain-specific features to do this task. Okay, so domain to vec, what it does is it learns a vector representation of a visual domain, so the entire domain, all the images in it, by extracting features specific to that domain via disentanglement, so via the technique that I just showed you. And so with domain to vec, we can predict domain similarities that match our intuition about visual relationships between different domains. So for example, in this case, for a satellite domain, we can map it into our domain to vec feature space and find the closest neighbor domain, which ideally, if this method works well, is also a satellite domain or something that's very similar to a satellite domain. And then we will use that source domain with labels to transfer knowledge to our new input domain. And again, because if we find a source domain that is visually closer, more similar to our target, it will have less of a domain shift between the source and target. And so even if we still do adaptation, we don't have to work as hard to bridge the domain gap and to deal with the domain bias problem. And so the problem will become easier for us. The problem of knowledge transfer will become easier. So just briefly, how we actually compute the domain to vec embedding is as a combination of two parts. The first is the average of the domain invariant features in the images of that domain. And the second is the diagonals of the gram matrix of that average feature. And so because the gram matrix is too large to use efficiently, we use the diagonals, and then we further concatenate these two parts and perform dimensionality reduction on top of that to, again, remove the sparsity. Okay, so that's how we compute the feature vector from a domain to compute its embedding. Now, to test this approach, we actually had to come up with a new data set that had lots of different domains in it, because most existing multi-domain data sets have maybe 6 or something like a dozen domain maximum. And so we wanted something with more domains to test this domain to vec embedding, because each point will be a different domain. So we collected a new data set that we call domain bank. And in this data set, we have something like, I believe, 56 different domains. And it's a composition of existing data sets. And it includes domains such as cars and real images, and also sketches, traffic data, synthetic data, logos, and so on. So it has a large variety of visually different image data. And so in our paper, we have lots of experiments where we, for example, use domain to vec to embed this domain bank data set. And then we can visualize it in this way where the nodes are domains and the edges represent the nearest neighbors in our domain to vec embedding space. And what we can see here is that indeed, some domains intuitively that we think should be similar, like face domains, are neighbors of each other in our domain to vec embedding. And some other domains that are very different, like sketch or logo, are further away from the real domains over here on the right, which are real photorealistic images. And so they get embedded further away from domains like sketches or logos. And so overall, we find that this embedding does sort of capture our intuition about visual relationships between domains. And we also evaluate using this method to find the closest domain and do domain transfer, and we show that it also works relatively well. Okay, so the last topic that I wanted to discuss is category shift. So far, we've assumed that in our source and target domains, the categories are exactly the same. But of course, in reality, we may have a source data set with labels for certain categories. And then at test time, we might get some new data where some of the categories are the same, but some are not. So let's say we're transferring from this image domain, real image domain, to a drawing domain, where some of the categories are the same in the source and target, but some other categories are missing in the target. And furthermore, some categories are completely new in the target. Of course, here we assume that we have no labels on the target, so we don't know which categories are missing and which ones are new. So can we still do domain transfer, and can we still transfer knowledge of the categories shared between source and target while also avoiding catastrophic alignment to these novel or missing categories? And so to illustrate this, I want to show you again this picture where we have a target domain. The blue points here are target images, and there's a category shift between them. So here the red points are source images that have the same categories with the target, and green points are the source categories that are not present in the target. Okay, so this is what it looks like before we do domain alignment. So what happens when we apply regular feature alignment, like some of the techniques that I just showed you, for example, domain discriminator or even class-based alignment? What is going to happen? So again, these red and blue points are source and target points from classes that exist in both domains. But the green points are from classes in the source that do not exist in the target, whereas some of these blue points in the middle are from classes in the target that are novel, and they're not present in the source. Let's see what happens in a category shift scenario when we do standard domain alignment. The resulting distributions look like this, where we see a problem because a lot of the blue target points are becoming aligned to green source points, which are classes that are not present in the target, so those points will be misclassified. So to solve this problem, we propose an approach that we call domain adaptation through self-supervision, or DANCE. And here is the resulting distributions with our method, where we can see that now we avoid catastrophic alignment of blue target points to those green source-only categories, which is the outcome we want. And we do this by both rejecting outliers in the target domain during alignment and also by using self-supervision to learn discriminative features on the target domain. Here's some small preview of the results that are in the paper. For example, we adapt from the synthetic domain to a real target domain where some of the categories are missing in the target, and compared to just training on the source, which doesn't do very well, or compared to state-of-the-art alignment methods, with our method, we achieve a 14% improvement in accuracy. And there are a lot more results on different shifts in our paper. To conclude, I have talked about different ways that we can mitigate dataset bias, including feature level and pixel level alignment, and some problems with those techniques and how we can solve them through doing weak alignment or partial alignment, or by respecting class boundaries by using the task classifier to align domains, and also doing feature disentanglement. What I didn't have time to talk about is other limitations of these methods, such as, for example, that they assume that we have a lot of unlabeled data in the target, which may not always be the case. And another thing they assume is that domain-specific features are not meaningful for the task, which also might not be true depending on the application. Finally, I'd like to thank my PhD students who did all the work that I talked about today, Danyun Kim, Xingchao Peng, and Kuniaki Saito. And I also would like to thank my collaborators at NVIDIA, MIT-IBM Lab, and sponsors NSF, HRI, and DARPA, and
Thank you very much for your attention.